All right.
All right.
Yeah, it should be recording now.
Great. Thank you. Um, yeah, so before I get started with this talk, I really want to do a little survey. And all you have to do is just raise your hand a little bit, okay? Just so I can see. So this is going to be a game of, right? Who here has? So if you have done what I'm showing on the slide, just raise your hand, right? So he who here in this class has used GPT or Copilot to write some code. Like raise your hand if you have. Okay, so a lot of people, I can see that. Great. Raise your hand if you've made clip art with Stable Diffusion or DALL-E or something like that. All right, a lot of people as well, maybe fewer people. Raise your hand if you have taken a ride in a self-driving car. Okay, a lot fewer people now because this is the self-driving cars are mostly in California. They're more, like a West Coast thing than an East Coast thing, and we're all East Coasters here. This is a video of a ride that I took earlier this year, by the way. It was really fun. And the last question that I have for you is raise your hand if you've had a robot clean your room. All right, so I see that there's not too many people, it's not too many hands raised up right now. But what I've been working towards, what I'm really excited by, is the possibility that we can get a robot, just put it there and have it clean your room. Now, let's think about how far we've come when we're trying to build this, right? If you're keeping up with the current news from industry, then you have a lot of reasons to be hopeful. On the top, I'm showing a video, came out very recently, like less than a month ago, from Boston Dynamics. There's a robot in a factory. What it's doing is it's moving engine covers between racks, right? Here's the rack that's horizontal. It's going to take it, move it to a different rack, vertical, and then it's just going to put it there. And then the bottom video that I have, this is from a startup called Physical Intelligence. This is a video for the robot. It's taking clothes out of a dryer and then it's going to put it on a table and it's going to try to fold those clothes, right? Both of those are very recent. Both of those are roughly 3 weeks old right now. But it looks like there's a lot of promise. There's a lot of potential for us to get robots that actually are there. They help us do all the things that we want to do, right? So if we have like a certain setup, a fixed setup, and we want a robot that just helps us tackle whatever challenge that we have in setup, we kind of have got this. We kind of have a way of building our system around this one particular scene, let's say a factory, where we want the robot to help us. We almost have a way in the future, maybe, next 2 years, 5 years, 10 years, to get these robots to help us in the way that we want to. But the question that I am more interested in is going beyond that singular setup that you have, let's say in your factory. Do we have a way to have robots that are just out there in the wild doing all the things that we want them to do, not just in that one particular environment? And this is one thing that I think we have not been putting too much focus or emphasis on. This is what I call this kind of endless cycle of just add data, right? Like I do robot learning, I do a lot of learning from data, and this is kind of the problem that we see. Here's one of our work. This is actually not that old. This is from 2022. At the time, it was a pretty big state of the art in conditional behavioral cloning, right? We taught this robot if it's conditioned on like open the oven door, right? Then it opens the oven door in the bottom, as you can see. So what we did, right, is this is what the training data looks like. What we did was we took a few different toys from around the lab, and then we put it all into the play kitchen. And this is what it looks like when we add this kind of distractor objects onto the scene. The robot, which was opening the oven perfectly, even though we have not modified anything close to the oven, it all of a sudden starts failing. Why is that? That's because the robot, when training, has not seen all of these distractor objects. So when those objects exist, it doesn't know what to do, right? And the classical solution for this is, oh, now you go back and you collect a little bit more data. And then once you have a little bit more data, you retrain the robot, and then the robot can handle this. This is fine, but this feels a little unsatisfying, right? Because elsewhere in machine learning, when we look at things, we really see that things just work, right?
Man,
So for
can you turn down the volume? You're louder in the next room than I am. Thanks so much.
sorry, Atish, could you repeat the question?
No, he was just asking us to turn the volume down. That's my bad.
Oh, okay. Sounds good. All right. But as I was saying, elsewhere, right? Elsewhere in machine learning and computer vision in natural language, things really just work out of the box, right? You can download, let's say, segment anything model, and you can have a picture of, let's say, cells, and then you can pass it in and it just works. You don't have to fine tune it. You don't have to, let's say, give ChatGPT 5,000 of your emails before it knows how to write an email for you. So the question is, what do we need? What is left until robots also just work? And this is what we're going to be looking at today. Now, if your recipe for this, for robots that just work, is that, oh, you just add more data until there's enough data that robots just start working out of the box, I have something to tell you, which is the scale of a robot data sets that we have are really, really small compared to the data sets that you have for, let's say, language models or computer vision, right? Here's, for example, a comparison between like largest public robot data set, some private robotics data sets, the data set that is GPT-2 trained on, and the data set that Llama 3 is trained on. And all of these circles are actually drawn to size. So you can get an idea of how little data we have for robotics compared to how much data we have for language model at scale at which it really started working, right? GPT-2 is the point where it's not quite working, but it has signs of life. And then you scale it up more than 1,000 times, and then you get Llama 3, right? So the scaling is really not in our favor if we really just want to go by, okay, we're just going to scale and things are just going to start to work. So at this point, when we know that just data may not be able to save us, what do we do, right? Is it all doom and gloom from out here? And what I'm here to tell you today is it's not all doom and gloom. There is hope that there are ways in which we can really get this. And so this is what I've been working my research on for my PhD. My goal has been always, I'm going to carry a robot. I'm going to take it to a random apartment. I'm going to carry it over. Again, this is New York, so we really carry it up. We don't have elevators. Carry it up 6 stories. We put it in a random home. And what I want is I want these robots to just work, right? Whether this is because you give it a query and it, like knows how to go and pick and place, or whether you're trying to train it few shot how to do work, or you're trying to teach it how, zero shot do a few skills that you've taught it how to do, right? And so this is what my work has been on. My work has been on figuring out the interplay between representation, data, and memory for robots that really just work out of the box. And so some of the things that I'm showing here, some of the things I'm going to be talking about today, they're zero-shot deployment, which means that you just take a robot, you unbox it, you put it in the environment, you get it to run. Some of the other works I'm going to be talking about today are going to be about few-shot models, right? So you give it a little bit of data, and then it learns how to do something very quickly. So without further ado, let me just jump in and start talking about the projects and the works that I've been doing. So this is chapter 1. Here I'm going to be talking about how do you take, large pre-trained models, some of it is, let's say, foundation models, some of which are not, and how do you combine them together to get zero-shot pick and drop in completely arbitrary environments, right? So this is what it's going to be looking like. How do I, for example, take a robot, put it in a random home, and then ask it questions like, hey, robot, move the Takis on the desk to the nightstand, right? And a bunch of different questions, but really you don't know what the Takis is, you don't know where the nightstand are. And all of these questions you have to answer without really having any experience in the scene. That's what I'm going to be trying to do here. I hope this part is clear. So what we do here, actually, is instead of trying to answer this very large, very big monolithic question, what we do is we take a question of this format and we break it down into few small pieces. So the first piece for the robot is going to be, how do I go to the Takis, right? Once you figure out how to go to the Takis, and again, this is an unknown environment, you don't know what Takis are maybe. Once you figure that out, you can navigate to where the Takis are. When you're in front of the Takis, you have to figure out, how do I pick up the Takis? And for example, people who don't know what Takis are, you are all in college or in university, so I assume you do. But Takis are these chips that I really like. So this is what the example I'm giving. So the second question then, when you're in front of the Takis as a robot, is how do I pick up the Takis? And then, okay, once you can pick it up, then you can navigate to the target, which is the nightstand here. Then you have to figure out how do you drop the Takis on the nightstand. Now, the part that you have to think about is that some of these problems people have really worked a lot on. So, for example, bin picking, right? Like picking up objects from a bin in front of you. This is a problem that they use really a lot in industry. So there are good solutions for this. So, for example, here's a video I'm showing from this paper called AnyGrasp, where you can give a bunch of objects in a bin in front of it, and the robot can just pick it up and put it in a bin next to it. So solutions like this already exist. But what the bigger question that is unsolved at the time when I was looking at this problem is really this kind of navigation in an open world given a random language query, right? The question of how do I get to the Takis where I don't know where I am and where I don't know what Takis are even. It could be any other object. It could be, like a baby Yoda. It could be anything at all. What we need to solve this problem is we need some form of map of the world that I'm in. Right? As a robot, when you were there, when you were trying to find this object, again, we're going to go back into this tested and tried idea in robotics, is we need a map. So let's talk a little bit about what those maps look like traditionally in robotics. Generally, when you're trying to build a map of the world in robotics, it may look something like this, right? It may be some sort of explicit memory, right? Where it's mapping from a location to some number of fixed classes, right? It could be like bed, toilet, TV, sink, oven, refrigerator, things like that. And you slowly build up a map of like what's where in your house. So here, what you see on the left is like a top-down map of some fixed number of classes. On the right, what you see is what we call an obstacle map, right? This map is telling you, okay, in this location, it is 0 if there's no obstacle, 1 if there's an obstacle. And then based on that, you can use your robot to navigate around. This is one kind of map. We call it explicit memory. Why do we call it explicit? Because it's explicitly mapping out location and properties. And the properties are some number of fixed classes. Another kind of map that kind of emerges is what we call an implicit memory, right? So imagine you have an end-to-end policy that is doing navigation. So it has a bunch of image going into the policy. And then you have, some sort of action or goal that is coming out of the policy. Like, oh, I want to navigate here, or I want to navigate there. So those are generally two different kinds of memories that we use, or maps that we use for navigation for robots in the real world. But they each have one problem that you have to struggle with. For the explicit memory, generally you have a few fixed number of classes and properties, right? So for example, when I'm showing like obstacle, not obstacle, when I'm showing like couch, potted plant, bed, toilet, things like that, you fix the classes that you're going to see ahead of time. And then you scan the environment, then you're like, okay, here's what where is. But then in test time, if you're given a random query like Takis, if you didn't scan for Takis, you don't know where the Takis are, right? So this is a problem. On the other hand, for the implicit memory, right, like if you're training a very large end-to-end model, the problem is you really need a lot of data and a lot of compute to train this, right? And it's hard to adapt it on a zero-shot manner in a new environment because what data are you adapting with? Right? So what we did here in this project is we tried to combine the best of both worlds. We tried to take explicit spatial memory, we took the structure from it, and then we took the implicit semantic memory, and we took the latent representation from it, right, in the hidden layers, and we combined them, both together into what we call the spatial semantic memory. And the idea for the spatial semantic memory is instead of mapping from each location to a fixed class or property, we're actually mapping to a latent vector. And this latent vector could be whatever dimensions based on what model you're building the memory out of. And so you can do some sort of very kind of open-ended queries that you couldn't do, for example, in the explicit spatial memory. For example, you can query for open vocabulary classes like black chairs. If you have a classifier, given the latent, it tells you like, okay, what is a black chair, what is not a black chair? Or you can classify for obstacles, right? So given the same memory, I can extract out what is the obstacle map in the scene. Or if you're doing some sort of exploration in the scene, you can get some sort of value function out of it, right? You can get like, okay, here's where you should explore if you're looking for the take chips. Okay, this solves the problem of, okay, how do we do open-ended queries on my map that I've built in, like runtime? How do we build this memory, right? Like without training. So that's the second part, which is how do you build the scenery representations in a zero-shot fashion? This is also possible because of all the advances in the vision language models that we made today. Here's how this goes. You start off with a bunch of posed RGBD images, and then you go from there. You use the RGB and the camera matrix to do camera projection. Use odometry to figure out where each of the points XYZ location is. Okay, once you have that, then you start working on the image. You use some sort of open vocabulary object detectors to tell you what all the things are in that image, right? So here you can see like a little, patches where it's like, okay, here is maybe a notice, here's a tap, here's a sink, so on and so forth. When you have this object masks and this proposed labels, you can actually pass them through some sort of pre-trained vision language models. It could be CLIP, it could be SIGLIP, it could be some sort of larger vision language models, but you pass them all through that model to figure out what is the semantic embedding for that object is, or of that point is. What you have at the end of this process is really a bunch of points and then an associated semantic label associated with those points. Do people have questions on this process so far? All right. Yeah. And the nice thing about this is that all of these models that we're using, they're all pre-trained, they're all out of the box. So we can just get them zero shot and we can like start working with them. There is nothing that we have to train per scene. These are all models we're just downloading from the internet. So once we have this structure, we can actually start querying things, zero shot, and we can start finding objects. So for example, in the scene, you can start querying for bed, plant, or a bunch of other objects, and it just shows up on the map. But more than that, because you have this kind of like depth data, you can combine them in implicit memory, and you can also build the obstacle map out of which you can start querying for paths, right? So it can give you an obstacle-free path to go from where you are to, for example, the Taki chips. Another nice thing about the implicit memory is that you can put whatever you want in this implicit memory. So you can, for example, do some sort of double checking. So if your query is yellow potato crisp, and if your implicit map is giving you a bunch of objects like, oh, here's all the potential locations for yellow potato crisp, you can keep images as well as the latents in your implicit memory. You can pass it on, for example, in GPT to ask like, oh, all the results that I'm getting, are those real? Right? You can do a double checking to actually reduce uncertainty. So once you have that, you can combine it with, for example, the grasping models that we have from before, right? So again, here's what the robot POV looks like. Here's what our bin picking algorithm gives you, the video that I showed you. And then here's what a language conditioned segmentation map looks like. So you can combine the grasp proposals with the segmentations, and you can get a proposed grasp. And once you have this, right, once you have a proposed grasp, dropping works kind of similarly. You go there, you drop with the heuristic. You can just take your robot, put it in a new environment, and you can start giving queries like, hey, pick up the blue gloves and put them into the sink. And this is what it looks like. While I'm showing these videos, I want to ask people like if they have any questions about what I talked about so far. I'm going to keep playing these videos. And, as this works in one environment, it is training free, so we can take it over to any different environment and we can just give it random queries of objects that exist in the scene. Here you can see a bunch of different scenes. We took it to a bunch of different apartments in New York, and we just gave it a bunch of different queries to test out how well the system works. Okay, as you were watching this video, any questions so far? And if you don't understand any part, I'm happy to go back and try to explain it again. All right, so I'm going to move on, but feel free to stop me and ask questions anytime, especially if you don't. Yes.
There's a question.
Oh, please.
So I was gonna ask, by composing all these models together, wouldn't it be like computationally expensive to perform each task?
His question is that like by composing all of these models together, wouldn't it be very computationally expensive to just perform any of the tasks that you're showing?
Yes, that is a very good question, and the answer is yes. So all the work that I'm going to be showing from here on out after this project, those models all run on the robot. But because these models are so heavy, we have to run it off the robot. So the robot has, let's say, a GPU machine connected to it through internet, And when it has a query, it like has to send it over to the GPU machine to get the answer. However, because a robot is moving around and because unfortunately our robots are kind of slow, that is not the bottleneck. Does it answer the question?
Yep.
All right. But other thing that I think you kind of have signaled towards is that when you're composing all of these models together, isn't there a problem of kind of a cascading failure? If one of these things fail, the whole thing will fail. And this is actually what we notice when we run these experiments out into the real world, is that there's this kind of like cascading failure that you see when you try to run these experiments with a lot of different modules. Here, for example, you can see the total 375 trials that we've run, and some of them have failed in the navigation phase, some of them have failed in the manipulation phase, as in picking it up, and some of them have failed in the placing stage. And there are all of these different ways that this thing can fail. However, the more interesting thing for us is knowing how things fail so we can make things better down the line using our memory. And so, for example, one of the small thing I can tell you how things fail are this kind of localizing wrong or no object. And it happens so that when you give queries, sometimes these queries can be very brittle. Sometimes you have to do a little bit of prompt engineering to get the right object. So for example, in the bottom, if you ask for gray eye glass box, it doesn't work. It does work, but if you ask for gray eye glass box, it doesn't work, right? Things like that can actually be very brittle. And it seems like the large models that we have are also kind of brittle. And if those models get better, hopefully our memory will get it better as well. And putting it all together, right? Because we can just run it out of the box. We could also take it to a conference. We took it to the Coral conference, just happened like last month. Actually, beginning of this month. And we could run experiments in the real world. For example, here, putting the like apple in a Red Bull. As you can see, my undergrad Peichi, who's running this experiment, who led this work, is moving the Red Bull around in the video as well. Like when he gives a query, he just takes a bowl and it moves in a different place, and it still works. So you can actually make this memory dynamic and online. All right. So far, do people have any more questions about this? If not, then I think I'll ask a question, which is, all right, great. This can zero shot do pick and place, but is robotics all about just doing pick and place? There are so many more things that we may want a robot to do that is just beyond like picking a thing from one place and putting it in another. And the problem with that is that it is really hard for us to do things that we can't just download off of the internet, right? Here we downloaded like the grasping skill off the internet, and we figured out what takis are based on like internet data and internet models. But what happens when we want to teach our model how to do something new? So the next part that I'm going to be talking about, the next project, is all about figuring out how to teach a robot how to pick up a new skill and pick it up quickly in a new scene with a new task. Right? For example, I bring the robot in my home and I want to tell it like, hey, put my socks into the washer. How do I teach it how to pick up my socks and put it in the washer without having to do a lot of work in itself? And what we're going to be doing here is basically falls into this behavioral cloning framework, right? It's a supervised policy learning where you have a data set of a lot of observations and associated actions. And you're trying to train a model connecting the observation to the action. You generally train it through backprop. Atiksha, question, are people familiar with supervised like behavioral cloning?
Yes, they should be.
All right, sounds good. So I'm not going to put too much time into this. However, one of the problem when you want to do behavioral cloning, especially into the real world, is the question of where's the supervision data come from, right? I want a data set of observation and action paired together, but where's this data coming from? So this is the problem of data scarcity. There's a lot of people with a lot of different proponents. Some people will say like, oh, let's collect data in simulation. There's, of course, you've heard of this problem of sim to real gap, which is a problem, but I don't think it's too big of a problem. I think you can engineer your way through this. I think the bigger problem is how do you model these diverse environments where you can learn and then you can deploy it in random homes. I think modeling real homes is really hard, especially after the scenes that I've seen going into people's homes, how crazy, how diverse it is. And what you see a lot of times here in the video that I showed you is you end up seeing a lot of kind of like empty homes, random objects. It really doesn't look like real homes. Now, if you're not doing it in simulation, if you want to do it in the real world, The other problem is that, like robots are heavy. You don't want to take a robot, don't want to put it in the home, and you don't want to like collect data using the robot itself, right? For example, here's the mobile Aloha setup from Stanford. It's a great setup, but unfortunately, it's not going to fit in through my door in my New York apartment. So what should we do if we want to collect data for robots into the real world, but we don't want to take the robot and then just hold it and collect data with it? There's this line of work that I think I've focused on a lot and I really like, which is called this kind of robot-free robot data collection. The way it works is that you use kind of some kind of custom end effector, right? So here, for example, a work from Sharon Song in 2019, they're teaching it how to grasp objects, right? And you use that custom end effector using a handheld tool to collect a lot of data. There's a lot of work that has been done in this line. So for example, this is from Sarah Young in 2020 in Berkeley. There is this work from our group earlier on in 2021. And all of this have kind of the same format. There's this tool, there's this camera, and you're using this tool to move around things in the real world. You're using this to collect data. There's even more work that has been done more recently. So there's some work from our group, there's some work from Stanford. So we call our work Stick V1. There's a Stanford work called UMI. You might be familiar with that. And there's a more recent work where we just refreshed our Stick tool. So the question is, right, like when you're designing one of these tools, when you are trying to use this tool to collect data, what are the main things that you have to worry about? What are the main things that you have to think about? And there are two primary goals that I'll tell you about using these kind of tools to collect data. The two goals look something like this. The goal number one is that you want to make this tool cheap, right? You want to make this tool cheap, easy to build, because you want to have a lot of these tools that you can put in a lot of different places because you want to scale up your data set, right? So you want this tool to be not super expensive. And the second thing is that you want this tool to be super easy to use, right? You don't want people to have a lot of expertise in collecting data because then you have to train these people, and training these people takes a lot of time and energy, right? You want this to be super easy. So those are the two goals. And I'm going to tell you like what makes those things hard. Making this cheap has two components. The component number one, as you can see, if you look at these tools, is that they have some part of hardware. This part is easy because you're building it, right? Like a lot of these tools, we literally bought like some sort of picking tool off of Amazon, and then we just use that. That's not hard because you're designing it, you can make it cheaper. The hard part in making it cheap is actually all of these tools have a camera with it. And because this camera, you're not making it, right? You're buying it. And because you're buying it, you're just beholden to whatever the market price. Like the cheapest GoPro is around like $300 or something, right? So that is where the bottleneck is when you want to make it cheap. The next part is making this easy. What makes this hard to do, right? A big part what makes it hard is really getting actions out of this data that you're collecting. When you collect data, this is what it looks like, right? You really just have a video. Here's a first-person video of like me trying to open a drawer, and you have to figure out what the robot should do given just this video. And this is not an easy problem. Generally, the way it's done is through some sort of algorithms like SFM or SLAM. These are really just using visual features to back out actions from these videos. And the problem there is that a lot of times there is not good visual features. And so what you have to do is a lot of calibration. So here's, for example, a video from the UMI page, right? You have to take it to a new environment, then you have to do a calibration process for 1 whole minute. Are people clear about what the difficult parts are in making this tool? All right. If people are clear about this, I'm going to tell you what we did to solve this. And this is one of those great moments in life where both of these problems of making it cheap and making it easy actually has the exactly same solutions. And the solution is actually in probably around half of your pockets right now. The solution is as simple as just this. What you do is you build your entire tool around your iPhone. And because you make it around your iPhone, you don't have to worry about the cost of like, okay, what's the price of an iPhone? Okay, if you have it in your pocket already, the hardware price is just $25. So you can just make a hardware with $25 and you can give it to people who has an iPhone. And the other part of making it easy for the calibration process is that the iPhone also has a bunch of sensors in it, right? It has RGB, it has LiDAR, it has gyroscope, accelerometer, IMU, a bunch of different sensors. So you can tie them all together and you can make a system where you really have to do no calibration whatsoever. So for example, here's like, this tool, we gave it to our colleague's dad, and now he's collecting data because he doesn't have to do any calibration. Just go in front of it, start recording, do data collection. All right, stop recording, done. Right? Both of these things really make the life a lot easier just because we're designing our entire tool around something that people already has, which already has a lot of sensors. And sure, like the iPhone's like what, $1,000 now, but again, hopefully people are not buying an iPhone just to collect data. They have a lot of things that they do, but sometimes they also collect data. And another nice thing about this kind of design is that you can get cross embodiment right out of the box, right? You can get the stick and you can take your iPhone, you can put the same system on a robot, right? As long as you have this 3D printed pieces and as long as you have like this two-finger design, right? The soft finger design. So we made mounts, which works with, for example, Hello Robot Stretch, which works with X-arm robots, which works with a lot of different robots. You just have to have 6 degrees of freedom on the arm, and you need to have like 1 degree of open and close on the finger. That's all you need. Do people have question here so far? All right, and feel free to stop me at any time. I'm going to move on. So what do you do when you have this kind of very easy to collect data tool in your hand and you can make a lot of these? What we did was we went around and we collected a lot of home data. I want to point you to the top middle where there's a cat in the back. I'll show it again. But what we did was we really went around into people's homes and we collected a lot of data. It's around like 13 hours of data in total, 22 homes, which is not a lot. But we got data from 216 environments, different environments. And that, I think, at the time was very large. Generally, robot datasets do not have so many different scenes. So then the question is, okay, now we have this data set. Okay, that's great. But how do we use this data set to accelerate learning for downstream tasks, right? Because our goal at the end of the day is that, okay, I want to bring this robot into my home and I want to teach it how to put socks into my washer. How do I do it quickly given that we have this data set? So we're going to go back into the pre-training fine-tuning format. How does this work and what is a big bottleneck for this? A big bottleneck for, again, behavioral cloning is that there's a huge information disparity on two sides of the learning. On the observation side, your dimensions, even if it's very small, 2024 by 2024 by 3, your dimensions are around 1.5 100,000, right? 150,000 dimension of data. On the action side, generally it's much smaller. It's something like 7 or 14, but really it's in the order of 10. And because you're trying to connect this data, which has a lot of dimension, to a data that has very few dimensions, you either need a lot of data or you need very strong priors to figure out like how to map this properly in a robust way that generalizes and not just like memorizes the data. If you're familiar with standard machine learning, this is, like the problem of like, how do you not overfit when you're training on a very small amount of data? What we're going to be doing is instead we're going to be looking into priors. What kind of priors can we put into this network? A lot of times what people do is they use some sort of pre-trained visual encoders, right? For example, starting with like a ResNet model or starting with like a CLIP or Dino model. There are people who have also trained like embodied robot data pre-trained models. However, one thing that these models, these pre-trained visual encoders miss is that we have a lot of in-domain data. Like we went around, we collected data in people's homes. How should we use that data to speed up the training for the models that we're going to see downstreams, which are also going to be in homes, right? And the solution for that is really self-supervised learning. Self-supervised learning, if you're not familiar with it, is just a process where you have only input, you have no output, and then you try to figure out some sort of invariant features in the data, and you use that learning signal to accelerate learning. In an earlier paper from 2021, we actually showed that if you train a model with self-supervised learning, you can actually use just those image features, and you can do some sort of k-nearest neighbor search on those features to figure out what actions you should apply, which really tells us that this feature learning and the self-supervised feature learning is where a lot of heavy lifting really does happen. Okay, so once we have this recipe of doing, let's do self-supervised learning, that's what we do with our data set. We train a Resident 34 model with SSL, Moco v3. And once we have this model, we use this model downstream in the homes to do fine-tuning. So here's what our few-shot deployment looks like. Step one is you collect 24 demonstrations in your home for whatever task you want to do. Here's, for example, uncle who wants to do drawer opening, right, in his home. So what he does is he collects 24 demonstrations, which around takes 5 minutes using our handheld tool. Okay, once you have that, you take our pre-trained model, you fine-tune this model for 15 minutes, okay, on the data that you've collected for 5 minutes. And once you fine-tune this model for 15 minutes and 20 minutes, you have this policy, and you can run it on your home. So here's a robot doing the exact same task that uncle was trying to teach the robot to do. And this, this is a full-on framework. This works. So we took it to a lot of different homes in New York City. Here's kind of little points where we show where it works. And we just ran a bunch of different tasks in all of these different homes. So here's kind of a video collage of all the different things that we've tried. Actually, this has 9 things missing. We tried a total of 109 different things, trying to teach the robot how to do different tasks in different homes. Again, these are very short horizon tasks, but this robot is actually able to learn all of these things. And here's, for example, bar chart showing like what is the success rate cumulatively. Overall, we find around 81% success rate on the 109 different tasks that we've done. But we see that, for example, for a lot of tasks, you really can learn this in a few-shot manner. And because this whole framework is so easy to deploy, we could also take it, for example, in New Orleans, in Europe, or for example, in Ikra in Japan, and we could get like a new toaster oven. We just got it locally, and we put it in the conference. In the morning, we collected data. In the afternoon, we demoed it to people, right? This is just that easy. We just have our tool, we collect data, we train a policy, we run it in the environment. Do people have questions about this whole framework so far?
I have a question.
Yes.
So you mentioned about like most of the tasks are like easier to or successfully deploy in future. Like, do you have any like conclusion on like what sort of features or conditions that makes it like few shots capable to the
Are you
task?
asking for the properties of the task, or are you asking about properties of the sorry, are you asking for properties of the task, or are you asking about properties of the system or the model?
I guess the property of the task.
Okay, yeah, so we actually did a very like rigorous analysis of like what tasks work and what tasks don't work. At the time, what did not work very well is tasks that involved like rotation in it. So if you had to do like some sort of precise rotation involved tasks, those tasks did not work very well. Another class of tasks that did not work very well is, for example, tasks which are hard to tell what is going on if you just have this like on wrist first person camera, right? So for example, like if you pick something up from here and then you walk over to the kitchen and like drop something there, this is a very long horizon task, and you don't have a view of the global environment just from your first person camera. That is another task that is hard to do just with very limited information. And that is another good question. Like we really need a good sense of memory to do this kind of tasks. But yeah, there are like more on the paper. I welcome you to like take a look at that. And again, like all of this is open source. So, if you have a robot, you want to do something few shot, you can like just, like download the system, collect a few data and get started on it. But yeah, like I encourage taking a look at the paper. We did a lot of analysis on like what works, what doesn't work. All right. All right. So any other questions? All right. So if there are no other questions, and again, stop me at any time when you feel like it, just, raise a hand and hopefully Atish will let me know. One of the questions that really came to us after doing this is that, okay, this is great. Now, like we can take a toaster oven, we can open it in Europe. We can take a toaster oven, we can open it in Japan, or like, buy a toaster oven from Japan and teach it how to open it. But really, how many times, right, do you have to teach the robot how to open a toaster oven until it just knows how to open any toaster oven, right? Because you don't want to keep doing it over and over and over and over. right? Like how many times do you have to do it before the robot just knows? Like, hey, it's a toaster oven, I know how to open it. This is a cabinet door, I know how to open it. How many times do you have to do it? So this is the third part. This is the part that I'm, like I've done most recently, I'm the most excited about, which is how do you teach arbitrary skills that it can just run in arbitrary scenes, right? Like how do you open any cabinet drawer in any environment? How do you open any toaster oven in any environment? How do you teach that? Of course, the step one, again, we're going through the behavioral cloning process. Step one is, of course, gathering kind of this diverse data set of, let's say, door opening or drawer opening, things like that. So that's what we did. And again, it's super easy because we have this handheld tool, so you can just go out and do it. We targeted 5 different tasks, right? Here are the 5: door opening. Door opening reorientation is just taking a bottle that, let's say, that's fallen over, and you pick it up and put it down. Back pickup and tissue pickup because we just wanted to test something different. We collected data from around 40 environments for each task. And again, because, like we're going with the same framework, we collected around 25 demonstration per environment. And once we have this data, right, what do we do with it? The most obvious answer, the most clean-cut answer there could just be, oh, you take this data and you train a large behavior generation model, right? You just train a big policy on this data and then just works out of the box. While that is a very nice and ideal thought, it just doesn't work, or it did not work before we addressed the problem. And this problem is a problem of multimodality. Let me explain it to you why that doesn't work. So imagine you want to model this large behavior data set, right? Imagine your task is door opening, and you have collected a lot of data for door opening. How would that data look like? Let me give you an example. Let's say here's the door that you want to open, right? And you go in and you collect some data, you just go for the handle, you hold it, you pull it back. Okay, great. That's like one way of opening a door. Awesome. However, what happens after that is you give the tool to your friend. And your friend, you tell them like, hey, can you give me some data for opening doors? And your friend's like, sure. So what your friend does is your friend notices that the door is actually cracked open a little bit, right? And what he does is he just goes around, like wedges the hand in the crack and pulls the entire door open. Both of those are actually valid ways of opening the door. Both of these are really like correct answer. But the problem is that now you have one question for which there are 2 correct answers. And the problem was that traditional behavioral cloning algorithms were actually really not equipped to handle this. The fact that sometimes one correct question can have 2 correct answers. And modeling this multimodality is key for like modeling large behavior or action data sets. And this multimodality can come from different sides. It could come from, let's say, different orders of doing the tasks. So here's another example of, let's say you want to open microwave, turn a knob, and then open the oven, right? And this is, like not that hard. This is, for example, one person collecting the data to do it. However, it could go in a different way. Someone could go and do these things in the opposite order. They could first open the oven, and then they turn the knob, and then they open the microwave. Both of those are valid given these commands that you've given them. You have like specified a right order. But when you're trying to learn from this data, you have to learn both orders. And this is something that previous algorithms were really not equipped to handle. Is the problem of multimodality clear to everyone? Is there a question? Sorry, I cannot see hands.
I have a quick question.
Yes, please.
So for the data that you collect on that, like gripper thing, how will it generalize like other types of like arms that use different types of grips? Is it like only specified to that one, or can it do other ones as well?
So this is a good question. I think one of the things that we have not looked into too much is like, what if it is the gripper is visibly different? Because when you have the gripper thing, right, and when you have the camera out here, the camera is still looking at the grippers. So when you switch out the gripper for some other gripper, it may be out of distribution. It may be like, oh, I don't know this gripper anymore. So that's one of the things that I think we have to figure out if we want to take it to a completely different end effector. However, one thing we have tried out is, for example, what if you make an end effector that fits onto different robots? And that's something we can do. That's something we have done already. So that is something that does transfer. We know that. Does it answer your question?
Yes, thank you.
All right. So once we are clear on the problem of multimodality, I'm not gonna linger too much more on here. The thing that I want to do is try to figure out how do we handle this, right? How do we build algorithms that can handle this? And what I did personally is try to understand how do other people in machine learning does it, right? So for example, how do large language models handle multimodality? And like if you're not familiar with large language models, which I don't think is very likely, the way that they do it is, like here I'm showing words, but they deal in tokens. And given a sequence of tokens, they try to predict the next token. But not just that they're trying to predict the next token, right? So for example, here I saw a cat on blank, right? They actually try to predict the distribution of next tokens, right? Instead of predicting like singular token. So it might say that, oh, the next token is mat with 76% probability and bed with 12% probability or tree with 2% probability. And this, I think, is a very good way of handling multimodality. If we want to import this into our framework, there's just one little problem. And the problem goes something like this. The objective that we're dealing with, we're trying to model actions, and actions are generally continuous. It is easy to learn discrete multimodal distributions on tokens, but it is hard to learn multimodal distributions over continuous actions. So how do we do it? Again, we can look at, for example, how LLMs do it. And let's say, how do they generate, let's say, images, right? Because images are continuous. Images are not discrete in the way the language is discrete. So how do they handle that? And what they do is they use this architecture called a VQVAE, or a vector quantized variational autoencoder. The high level idea is very simple. You have, again, an autoencoder. That encoder goes in, some latent in the middle, decoder goes out, gives back the original data. And then when you have the latent in the middle, you try to quantize it, right? You try to make it fit into a few discrete bins. And once it does that, then you can use language models to actually generate those discrete bins. We can actually take the same trick, we can apply it into our action generation setup. We can do something like action tokenization with VQVAEs, right? So again, same setup, you have encoder, you have decoder, you have some sort of latent in the middle, and then you can use some sort of latent code book to bin all your action latent into discrete bins. And then once you have these discrete bins, your action has a discrete representation. And if your action has discrete representations, you can just very easily learn multimodal distributions over this, right? Because again, discrete means that you can learn categorical distribution, which means that you're done. So the question is, if you just do this, does this work? All right, I want a show of hands from people who thinks that this is just going to work and is going to solve all of our problems. All right, not too many people are raising their hands. I think that is because people have already said that this, just naively put, will not work. Maybe I've led the question a little bit. But yes, the answer is it doesn't work. In behavioral cloning especially, small errors really add up. If people are familiar with Dagger, this is the same problem, right? If your actions are discretized, what happens is that they miss out a little bit on the tokenization process. And when you have an action that is very close, but not exactly the right action, your small errors actually keep adding up. And they keep adding up until you have the setup where, you're actually very far away from where you want it to be. Here's, for example, a simulation video. I'm not going to run it in the real world, but in the simulation video, you can see the robot missing the kettle for a little bit, and then missing the knob that is trying to turn also by a little bit, just because the actions are not exactly right. They're right, but they're slightly far away. So what we have to do is actually use a couple of different algorithmic tricks to make this work in this continuous setup where the accuracy is really, really needed. The resolution is what really makes or breaks it. So there are two ideas that we're going to be using to fix this. Idea number one is hierarchical tokenization, right? This is just really understanding that you can use more tokens, right? More discrete tokens to improve the resolution of the action that you're getting. Before I talk about this, I have a question, which is the idea of tokenization, right? Converting continuous actions to discrete and then discrete tokens to continuous actions, is that part clear to people? All right, so if that part is clear to people, then we can go into the next bit, which is how do we do a tokenization with more resolution, right? So for example, here's an image that you can see of, let's say, two-dimensional actions. How do they look after detokenization, right? Okay, they have some resolution, but they're not as dense. What you can do is you can take the residuals off of those like learned latents, and you can tokenize the residual itself. And when you tokenize the residual itself, you can get a much denser decoding by using two tokens instead of one token. The first token is for like the higher level actions. The second token is the residual actions. So you can use two tokens instead of one to figure out, okay, what is a little bit more dense representation for your continuous actions. That's step number one. And then step number two is what you can do as well is predict some sort of continuous offset. Here's what it looks like, right? So imagine you have a continuous signal, and you discretize it with some number of bins, let's say 10 bins. You have a little bit of an offset that is left over that is not captured by the discretized signal. What you can do is you can use your network to predict that as well. And again, this residual always remains, even if you're doing residual tokenization, because, like you are more accurate, but this offset is something that is always there. So what you do is you learn an extra head to predict that continuous offset on top of the discrete tokens. However, this offset is very small, and generally this offset is not multimodal, so you don't have to do all the fancy stuff to do multimodal prediction on top of that. So put it all together, what we do is we make this algorithm called VQ behavior transformer, which models behavior like GPT. The high-level idea is very simple. You give it a sequence of observations, right? You put it to a sequence model, and then on the output side, you get some tokens. You sample some tokens, and those sample tokens are representations of your action. Once you have the sample tokens, right, you can train this with, for example, ground truth actions. You put the ground truth actions continuous through the VQVA encoder, and you get some discrete ground truth tokens. And you regularize the network with the categorical loss that you get between the sample tokens and the ground truth tokens. And when you want to sample actions, when you want to run this policy in the real world, you can pass it through the decoder and you get your continuous predicted actions out. More than that, because we want to get really precise actions out of it, we can also add offsets to the architecture, right? And so when we get sample tokens, we also predict the offset for each of the tokens. And then we regularize this offset values by an L1 loss, right? We put the ground truth actions to the tokenizers and we get whatever offset is. And we use an L1 loss to learn that with the network. Is this part, how we learn this whole thing, how we sample actions from it, is this clear to everybody? All right. If this is making sense more or less, and again, feel free to ask questions at any time. Oh, sorry, is there a question?
I don't think so.
Okay, sounds good. All right, so once you have learned this model, once you have, had a lot of data and you've trained this VQ-BET model on top of this, you can actually sample this to generate multimodal actions. So here, for example, we are starting a robot from the same location and we're running it twice. The first time it goes and it opens the right door. The next time it goes and opens the left door, right? Because on the data, it has seen both like opening left doors and opening right doors. So when it's faced with two doors in front of it, it just opens one of the two doors and random, just because you're sampling it from the learned behavior. Does this part make sense to people? All right, cool. So if this part makes sense, then we know that we have a model, we have a policy class that actually captures the diverse data that we've collected, and it can actually capture the multimodality that is in the data set. And we can actually train a large behavior generation model. So that's what we do. We take our 5 data sets and we put our behavior generation models, like behavior, like data through it, and we train these models that we call robot utility models. These models, again, they're trained on a single task data, right? So each model has its own data set, one for door opening, drawer opening, so on and so forth. And once we've done this, we also want to test this on novel environment, novel scenes, because that's what we're going for, right? We want it to open any doors anywhere or any drawers anywhere. So what we do is we order some evaluation scenes that was not in the training set from Amazon. We get, for example, random drawers that we can order off of Amazon, or put our robot into random corners of our lab for example, the tissue pickup task. We get all of our tissue boxes from Whole Foods because, again, that was not in the training set, and we test it, right? And the goal, again, is we want to get success in unseen objects and unseen scenes, right? Completely new scenes, completely new objects. We want to get it to work. And as it turns out, it does, right? So for example, here's sample rollouts from 5 different tasks. These are in our labs, but like this robot has never actually seen this environments before, but as long as you put it there, you run it, it just works. And again, compare this with the very early slide that I showed you, where in a kitchen you added some random objects and then the robot just doesn't work. These are completely new scenes, new objects, it just works. The results, if you look at, like the success rates of it, it looks roughly 75% out of the box, right? However, there is something to be said there about like what these failures look like. So before I actually tell you more about it, I want you to watch this video and think about like what could be done to make it better. So here's, for example, the robot. We took it into an Airbnb. This is a new drawer set it has never seen. And now we're trying to get it to open this door. All right. So far, given how the robot has failed, do people have ideas on how to fix it or how to make the robot do better? This is actually an answer that I gave out a few slides ago, if you noticed, which is this policy that we've trained is multimodal, it is stochastic. So what happens is if you run it multiple times, it may be able to succeed while it failed in a single rollout, right? Like again, remember when we ran the robot from the exact same state and it opened the right door once and opened the left door once. Here, if it even failed in drawer opening once, if we run it multiple times, it might actually succeed. But how do we figure out, right, that we can run it multiple times and it would work, right? How do we figure out, like, for example, it's not in a state where you can't run it anymore? Or how do we figure out that, like, oh, it's super easily fixable if only you could just retry it? So what we do instead is we use a verifier and we retry if it tells it so. This is actually a very common trick, for example, in code generation, right? Like imagine your model has written some code and then you run it through, like, let's say the Python interpreter. And the Python interpreter tells you like, oh, here's like indentation is wrong here. Okay, great. You can put this data back into your model and then the model can generate code which is better next time around. What we do here is very similar. Instead, we flip the recipe on its head and we use a multimodal LLM for the feedback, right? And we do it in the open world, which is why we need kind of this model that has seen a lot of different setups. So we ask the question of like, oh, in this pictures that you see, we take pictures from the head camera. We give all of this to the LLM and we ask like, hey, did we open the door successfully or not? And here, as you can see, that the door is not open. So the LLM says no. And if the LLM says no, then we just reset and retry, right? Resetting is just going back to the original position where you start executing and then running it again. So here's what the robot's going to be doing. And just this very simple trick of knowing when you should retry actually gets our success rate from 75% to around 90%. And yeah, this is a very simple idea. Like ask a verifier, Ask it if it's done. If not, you can try again. If it's in a situation where you can try it. Does this verifier guided retrying part make sense to people? Cool. So once we do this, right, we can actually run a lot of experiments in a lot of different places, and we can actually start building out rules. Rules you should follow when you're trying to train this kind of like generalizable models, zero shot, that you can just put out there in a different environment and you can start running it. So here are a few lessons that we learned. Lesson number one, of course, is, like you need a lot of data, right? It's not like 25 demonstrations anymore. You need a lot of diverse data, right? It's not just you can collect a lot of data from the same environment and expect it to work. For example, we went out and collect data from 40 different environments. That is also important. And the last piece that is important that might be surprising to you is you don't want to mix good data with bad data. Those are the three lessons, and I'll explain and I'll show you some results supporting why we do this. So the question number one is like how large of a data set do you need? How far can really scaling go? And here we ran using the same data set to different algorithms, diffusion policy, which you may have heard of, and Vicky Beaver transformer. Uh, we ran some tests on 3 different tasks where we scaled the size of the data set. And as you can see, for some tasks, the scaling seems like it has more room for improvement. But on other tasks, for example, reorientation, it seems like it's plateauing a little bit, right? So it seems like for not all tasks, we're hitting a saturation point, but for some tasks, we might be. So that's one. The second thing is what kind of data do we need for training this kind of policies? And what we say is we need a diverse and high quality data. Both of these are important. So first, diverse, right? Do we need diverse data? So here's an experiment. What we did was we have 2 data sets of the same size, 1,000 demonstrations each. One where we have 25 demonstrations in 40 environments. Another one where we have 200 demonstrations from 5 environments, right? Both of them are the same size. One is more diverse, but another one is more dense. You have more data from the same environments. And when you train on the diverse data set, whatever performance you get, we see that consistently it is much lower performance to have trained on more dense but less diverse data. And it is more severe in especially the tasks where the physics is more diverse. For example, object orientation, the bottles could be of different shapes, right? The physics could be different. It might have water in it, might not have water in it, so on and so forth. So there you really need a lot more diverse data than what you need in, for example, door opening. Because again, door opening physics is much more simpler. You can open doors to the right, you can open doors to the left, you have a handle, you have to just grasp it. So that's why we say that you need a lot of diverse data. Why do we say you need high quality data? Let's see what happens when you have high quality data and low quality data. And clearly, high quality data is better. Duh, of course, right? This is like to no one's surprise, high quality data works better when you're trying to train a model. But then there is this idea for co-training, right, that is espoused in a lot of recent work in the field, where you take all of your data, whether it's good data, bad data, you throw it all together, you train a large model on top of this. And what we see actually happens is that for some tasks, while it performs better, for other tasks, it actually hurts the performance. All right. So even if you have high quality data, if you throw in a bit of low quality data in it, sometimes it can actually make your performance worse. And this is what we see when co-training. So this is our recommendation. When you're trying to train model on it, really try to make sure that your data is high quality. You're not really mixing in any of low quality data in it. And once we have those, right, once we have the full recipe, once we have our policies, we can take it and we can run it in a random Airbnb. So here's, for example, a few different tasks. I'll take any questions that you may have on this as the video plays out. Do people have any questions so far? I think I want to ask at this point, have you had a chance to get the quiz done?
Yeah, I just went ahead and grabbed like everybody's like IDs basically.
Oh, okay, great. All right, awesome. So
Great.
we don't have to worry about that.
No, you can just go to the end.
All right, sounds good. All right. So again, these are all policies that we've trained, like nowhere close to this Airbnb, and then we just took it over into this random Airbnb, and then we got a bunch of supplies from Whole Foods, and then now we're just running these policies. And again, like these are policies that you can download today from the internet. And if you have a Hello Robot stretch or you have this like printed out wrist, then you can just run it on your own robots. And like hopefully this should work as long as there's, like as long as it's something the robot can physically do, not like a very heavy object or something like that. So yeah, so that's kind of like the high level idea for the utility models that we've trained. And again, because we call this utility models, you can just take it to, like a different place, different environment, entirely different country as well. And here, for example, we just went to Coral in Munich. We got some new cabinets from IKEA. We set it up. And then the next day we demoed on that cabinet, right? On how to open doors, let's say, and how to open drawers. This is Hariteja, who was my co-lead, who's an undergrad at NYU, leading this project with me as well. And like again, now we have ideas on how to make this kind of zero-shot policies that work in the real world. And just building on top of that is what's next. So let's talk a little bit about what is next, right? What are the things that we can do now? And what are the things that I'm most interested in? What are the research questions that you may want to think about? One of the easy things, one of the clearest things that I think that comes up from this work is really, general mobile manipulation that is anywhere, right? You want to take your robot, you want to put it random place and goes around, and then you can maybe ask it for like, oh, grab me this thing from the door. We're getting close to it. We don't have like a full project, but I think that is something that should be possible. You train the little skills, and you have your whole entire scene memory, and then the robot goes around and like it applies those skills into like local contexts and does things. That's something that I think should be possible, and that is something that I think should be very exciting. Another thing, for example, is like as I said, we don't have a lot of data. But I think looking at the data is not the right thing to do, because I think what we should be looking at is how well can we compress the data. Because compression, I think, is proportional to intelligence. If you look at the model sizes, right, like robot utility models that we train are around like 112 megabytes versus Llama 3 is like 140 gigabytes. The question is, how much data are we fitting into this size of model? And maybe we need to look at like how do we compress other things better? How do we even like add on features from Llama into the models that we're training? That's one of the things that I think would be very, very interesting and exciting. There's, for example, like interesting things in hardware world going on that we can do with, for example, the latent action training that we did for VQBet. Here's a hand, the hand that you're seeing. This is actually running with pneumatics. So this is not a traditional robot hand. It uses like water pumps to move the hand, and it's really hard to control because the control is nonlinear. So the question is, how do you do that? Or for example, on the right, you can see some tentacles, right? How do you control that? There's no real way, no clear way of controlling this. All of these questions are open questions in the future that I think would be very exciting to address using the framework of robot learning, using the framework of like, oh, we learn representations, we use our memory, and we use a reasonable bit of data to solve this. And that's what I've done so far. That's what I'm looking forward to in the next. And if you have any questions, I'd be happy to take. Otherwise, that's kind of the end of my talk. Thank you. All right. Any questions from people? I'm happy to take those as well.
I think most of the people are good.
Sorry.
I'll send you the recording
Mhm.
shortly, and then yeah, I think great lecture. Thank you for hosting the great guest lecture.
Yeah.
Yeah.
No, thank you. It was great. And like if any of you have questions as well later, just share my
and
email address.
if there's any questions, I'll send them like email by for you, like anything
good.
that comes up on our discussion board or anything. But yeah.
Yeah. No,
Thank you.
absolutely. No, thank you so much.
Let me just save the recording, and then